All right, so with that in mind, let me write a bunch more I's and J's to kind of summarize where we left things off. So what we had figured out kind of by the end of the last lecture is that we can write down these Hamiltonians between trapped ions as a sum on Jij, sigma ix, sigma jx. And these sigma x's are the Pauli operators. So this is the Pauli x operator acting on spin I, Pauli x operator acting on spin j, and these ions I and j are coupled with the strength Jij, which is capital Omega squared times the recoil R, sum over the modes, k equals 1 to n, Bik, Bjk, divided by mu squared minus omega k squared. So I had this on the board maybe 10 minutes ago or so, and I'll point out just maybe one thing or start to emphasize something a little bit more than I did last time, which is to say that out front here, this is the Rabi frequency. And for now, and for the next maybe 30 minutes or so, I want to consider that this is a global Rabi frequency. And by that, I mean, imagine that I have 2 ions or 10 ions or 100 ions, doesn't matter. I have these electric fields that I'm putting on, these bichromatic tones that hit all of them uniformly. Okay, so imagine this as being one big global beam that hits all of the ions, right? And this is kind of the lead in. I think it's intellectually simpler to understand as we get in. If you really want to kind of build a universal quantum computer that can do everything, run Shor's algorithm and all else, you absolutely can have the flexibility where ions I and J get their own Rabi frequencies. And in particular, maybe ions 2 and 112 in a chain get some Rabi frequency and all of the rest have a Rabi frequency of 0, so they don't participate, right? So that's way in the future and all that. For right now, I'm just considering one big beam that hits everything.
Can the Rabi frequency be time dependent?
The Rabi frequency can also be time dependent. So I won't talk about it much, but historically in trapped ion simulation, there have been experiments, for instance, that turn different pieces on and off, and you do that by changing Rabi frequencies. There have been adiabatic kind of protocols where you start with one Hamiltonian, or at least a part of a Hamiltonian, you kind of make it smaller as a function of time. Really, all that's accomplished by taking the Rabi frequencies and making them time dependent. Okay, yeah, so let me add one more caveat then from everything I'm going to discuss for the next bit. They're global and they're stationary. Okay. So this is what's going on in terms of coupling. I also drew this kind of picture in frequency space. So here we have omega 0. Sometimes this gets the jargony term of being called the carrier. And then we have the frequencies that you can excite by flipping a spin and adding a phonon. These are often called the blue side bands to the carrier. And then on the other side, we have all of the frequencies where we can flip a spin, but subtract one phonon, and these are the red side bands. We put on our electric field that has 2 colors in it. And so our electric field sits there and there, and it's detuned one of the colors by plus mu from resonance, and the other color minus mu from resonance. Okay. So this is all just from 12 minutes ago. Right. So this is our starting point. And now I want to start asking, if we stick with this example, what can we do with it? Or maybe before what we can do with it, how should I start thinking about these Jij interactions, right? What do they look like if I go to the lab and I dial in everything exactly as I've shown you, right? So I have a collection of ions. Those ions have these normal modes. I put on these bichromatic beams so that I have these 2 colors and plus mu and minus mu relative to these red and blue sidebands. What do we expect to see? Okay, so let me take down the screen here. Okay, so here I've done a calculation just with 3 ions to get our feet wet. So with 3 ions, you have 3 different connections. Okay, so you have J12, J23, and J13. Okay, so that's the connections between ions 1, 2, 3. And here it's just kind of a simple matrix where I can go through for some global Rabi frequency and ask, what's the connection between ions 1 and 2, ions 1 and 3, and then ions 2 and 3. And kind of what we find is that these nearest neighbors, J12 and J23, they're these red bars here that are relatively strong. And then that J13, where the 2 ions are about as far apart as you can get them in a 3-ion chain, the connection there is a little weaker. All right. I can do that again for 7 ions. Right? And it took longer than I care to admit to make all the connections there, right? But this is fully connected. All right. So every ion talks to every other ion. And here we can make kind of a similar calculation. We notice something pretty similar once again, which is that the nearest neighbor interactions, okay, J12, J23, J34, 4, 5, 5, 6, 6, 7, those are the strongest interactions in this chain. And then as you go to second nearest neighbors, third, fourth, fifth, sixth nearest neighbors, then interactions between those ions, they seem like they are trailing off. Okay, so we have something that might feel a little bit intuitive here, is when we arrange the system so that we put on these 2 colors outside of the blue and the red side bands, that we get this all-to-all connectivity. And the connectivity seems to, even though it's all-to-all, the strength seems to decrease somehow as the ion further into the world. Headline idea, is that okay so far? So now I want to investigate a little bit more closely. What is the true nature of this interaction? So we said that the interaction kind of falls away. The interaction gets a little bit weaker as we go further and further away in distance. But I want to understand that a little bit better. Right? So what I'm going to plot here is Jij versus the magnitude of I minus j. Okay, how strong is the coupling as a function of distance between pairs of ions? Okay, if I do things exactly like I've laid out. Okay, so here's the magnitude of I minus j. So I can think about nearest neighbors as being separated by kind of 1 lattice site, and second nearest neighbors, third nearest neighbors, and so on. Here's Jij, and I can do an exact calculation and make a couple of points on this plot. All right? And then what I can do is come along and start drawing things on this plot. For instance, I can draw a line like that. And notice that that line is a power law, Jij, approximately equal to some overall scale, J0, divided by the distance, I minus j, to the alpha power. All right, so these points come from the calculation right here. I have a harmonic trap. That means I have normal modes. I've got these colors, mu, plus mu and minus mu, and then I can calculate everything I need to know about this Jij. Those are the dots on that plot. And then what I can do is come along and notice that a power law, something like J0 over I minus j to the alpha, looks like it's a really good representation of those dots. Okay, now let me, really highlight this at the outset. Am I just a bad drawer in the sense that that line should have exactly gone through these dots, and it didn't, and I missed it? It turns out I am a fabulous drawer. And in fact, there is a little bit of a miss. Okay, so this is an approximate power law. Right? So if you ask, should this identically be J0 over some distance to the alpha power? The answer is no. It is approximate if you're interested in kind of the qualitative features, what's going on in some, let's say, many-body system with a power law decay. This is a great approximation to that. You can learn a lot of physics by doing it. The power law is not exact to 8 or 9 decimal places here. Okay, there's a little bit of a miss of usually of order of percent, maybe 2%. All right, so you should keep that in mind, that this power law, and whenever you talk about power law interactions and trapped ions, take that with a 1 or 2% fudge in there. Got invited more questions. I hope that was going to answer a few. Let's go for it.
Could you comment on the dependence of the I index itself rather than both the I minus J?
The dependence of the I index. Oh, yeah. So I guess if you're asking, if I look at nearest neighbors, right? So it is also possible in these kind of systems that, let's say, the JRJ interaction, let's say the interaction between ions 1 and 2, those are nearest neighbors, and ions 6 and 7, I don't know, in some big chain, even though they're nearest neighbors, they might also be a little bit different from each other. And so really what that means is, if I kind of come back over here to this spot and I ask for nearest neighbors, what are all of the possible JIJs that I can get? J12 might be here, and J23 might be there, and J34 might be there. Okay, there's going to be a little bit of spread in these points as well. So when we talk about these things kind of decaying like a power law, to find the power law, usually what people do is they average the nearest neighbor, the next nearest neighbor, the third nearest neighbor interactions. They fit 1 over R to some power to it and ask what power is the best fit.
Or then if you assume very long chains of ions, then the power can be exact.
It still won't be exact. It'll be a very good approximation, but you will have kind of the spread in points, and because of that spread, that line will go through every point exactly.
What I mean is just assuming infinite chains of ions, so that the fluctuation will be electric fluctuation.
Yeah. So even in the case of an infinite chain of ion,
So my question was, is the power law approximation because of some uncertainty? Like, say, I consider you have the nearest neighbors all lined up. Now, suppose if they were not lined up, they were all distinct, would the power law still be approximate? Or is there any fundamental reason why the power law is approximate and not just uncertainty in the way of saying?
all right, better again? Yes, thanks. Okay, so I would look at it the other way, which is to say the JIJs are given by this equation. And I can't look at this and say that's obviously something power law. Okay, and in fact, I don't know of any math that inherently says that this needs to turn out to be a power law, right? It's kind of an empirical observational property that when you put the dots on this plot, they can be well approximated by a power law. But I don't think that there is anything underlying that kind of forces or makes you expect that there should be one. Although maybe I'm going to modify that statement slightly in about 20 seconds.
So maybe a relative, how tunable is alpha here?
Okay, great. Next 20 seconds. I'm going to get there in 10 seconds.
Okay.
So the way that we tune alpha is actually pretty easy for us. The way that we can tune alpha is by taking these colors, plus and minus mu, these bichromatic beat note, and just changing. Okay. So depending on the value that we pick of mu, this alpha becomes tunable between 0, less than or equal to alpha, less than or equal to 3. Okay. And let me kind of show you where those limits come from. Okay. And in fact, those limits, those 1 over r to the third and 1 over r to the 0, those are exact power law limits. Okay. And let me kind of give you some intuition where they come from. First, the 1 over r cubed. If we take 1 over r cubed, we can get there by taking this value of mu and sending it all the way to infinity. All right. So we now have made mu equal to infinity. We come back to this Jij equation. We really kind of shot ourselves in the foot here because it's in the denominator and we have to square it. So our interaction strength is not going to be awesome. But here it is. What we end up with when we send that mu to infinity and you kind of sum over all the modes is really just kind of back to the natural dipole-dipole interaction between spins. It's about as slow as you can possibly get in ions. but it's there and it's like an interaction that goes like 1 over r cubed. Okay. The better thing to do is to take that mu, which was out at infinity, and imagine bringing it into something much more reasonable so that you can get some reasonable coupling strengths. And if you kind of push it all the way to the other limit, right? So if you push mu so that you're right on top of the center of mass mode, okay, when you're right on top of that center of mass mode, that means that you're very, very strongly exciting the center of mass mode, okay? So its contribution to Jij is huge compared to everything else. And a center of mass mode is when all of the ions are oscillating together with the same strength. Okay, and so if everybody is oscillating with the same strength together, then that looks like a 1 over r to the 0 interaction. That's all to all, everything is equally as strongly coupled to everything else. Okay, so those set the endpoints. When your mu is right on top of the center of mass mode, you get 1 over r to the 0. When mu is sent to infinity, you get 1 over r cubed. And if you vary mu anywhere in between, then you get this approximate power law like 1 over r to the alpha, where alpha is between 0 and 3. Sound good?
In the way you have it written down right now, it looks like in the limit, mu goes to 0, so you're at the carrier, not at the center of mass mode.
Sorry, mu goes to 0 detuning from the center of mass.
Okay, so
yeah, mu goes to omega center of mass.
Okay, so then it's possible for mu to go to the carrier.
Yeah, and yeah, so it is also possible to put, you can put mu anywhere you want.
Yeah.
Really what that's going to do is then change, which specific modes you couple to and with which strength.
Right. So I guess then you, would you call 0 the lower limit of your alpha then?
Yeah, so, okay, so what happens, let's say you continue changing mu. So let's say you put a mu there or somewhere over here. Totally allowed. This plot starts to kind of look nothing at all like a power law decay. And in fact, what you can get, let's say you're kind of on the, so this lowest mode, for instance, is a zigzag mode, okay, where one ion moves up, the next ion moves down, the next ion moves up. If you were to couple strongly to that mode, then if I were to make a similar sort of plot and ask what is Jij as a function of distance, then what you would find is that nearest neighbors will be coupled with some strength. Next nearest neighbors will be coupled with an opposite strength, a negative J, and then next nearest neighbor with positive strength again, and that zigzagging thing would be inherited in the Jij coupling structure. And so if that's something that you were interested to do a simulation or with, then in fact you can encode it. It'd be so hard.
Yes. But actually, I thought you don't want to excite the whole. Actually, you want to detune. You don't want to go.
And then that's the final thing, right? So this 1 over r to the 0, where I said, tune right up next to the center of mass mode, that itself is a little bit of an artificial limit, right? Because if we want to be in this limit where we're only virtually exciting the phonons, then we do need to keep some detuning. So even though this is often what you'll see kind of sometimes in the literature or out there that it's tunable between 0 and 3, much more practically, it's rare to see ion simulations where this power goes much below 0.5 and much above 2. And for both of those reasons, if you go too high here, then the coupling strength goes to 0. And if you go too low, then you're making too many phonons. Okay, so everything that we've been talking about has been with global beams, okay? And this is not nearly as far as we could push things, still with global beams, all right? And one of the things that we can do is to kind of exploit this frequency degree of freedom to say, even with a global beam, we can put on multiple bichromatic tones, all right? So by that, I mean, so far, I've only considered putting on bichromatic tones mu so that they're there and there. But imagine if we can address the single global beam with a whole bunch of frequency components, so that not only do I have frequency components there and there, but maybe there and there, and then also here and here, and then maybe here and here, and I'm also trying to draw them all with different amplitudes. Okay, so if you have an arbitrary waveform generator, then you can add as many tones as you like, and all of those different tones that you add can be of different phases and different amplitudes. Right, you have full control of engineering the frequency spectrum of this whole big global beam, that's a degree of freedom that can still be exploited. So let me modify this just by a little bit, because everything we've been talking about has been so far global beams with one pair of frequencies. And now I'm broadening this to say, what if we have, right? So in other words, now consider that we have capital M pairs of bichromatic tones, or bichromatic frequencies. And each of them, we're going to give them their own frequency and amplitude, so that our Jij is equal to sum over the modes, just like before, from k equals 1 to n. But now I want to also sum over the tones, m equals 1 to capital M, of omega m squared times the recoil times bjk over mu m squared minus omega k squared. All right, so this is identical to before, except now we're allowing there to be multiple frequency components, and each frequency component has its own amplitude and its own detuning field. Does that make sense so far, what I'm looking to do here? Still just one big beam that hits all of the ions. Okay. Once we have this kind of, I'll call this multi-tone driving, once we have these multiple frequency components in our big global beam, there are a whole bunch of new possibilities beyond these kind of approximate power laws that I've been talking about so far. Right? And so to really kind of see where some of the gains can be, I want to define a few more quantities and manipulate our expressions just by a little bit. All right, so to do that, let me define a new quantity. So let me define Jij with a k in the superscript as equal to bik bjk. Right, this part right up there. And really what I'm looking to do in spirit here, this is the kth mode contribution to the overall Jij matrix. Okay, so this is just a property of the normal modes. And then simultaneously, let me define C sub k is equal to the sum from m equals 1 to capital M, omega m squared times capital R over mu m squared minus omega k squared. This is the coefficient, or as I like to call it, the weight of the kth mode in the overall Jij matrix. Right, so it's a couple of definitions, but I like to take a step back and just kind of tell you what I'm after here. I've got this expression for Jij. It depends on normal modes, it depends on detunings, it depends on Rabi frequencies, it depends on starting to look like a lot of stuff. I want to simplify this intellectually to say that whatever Jij matrix I have, whatever couplings I've generated between spins I and j, it really only has two contributions to it, right? One contribution is the normal mode stuff that I'm calling these JK matrices. This contribution says how much of each of these normal mode pieces do I add up to get my overall Jij? Okay. And so with these definitions, I can write my overall J matrix as a sum over the modes k, going from 1 to n, of C sub k, jk. All right, so really the way that you should think about this is that these jk matrices, this is like a set of basis matrices. The only things that they depend on are the ion normal modes. And then once you have this basis of J matrices, you then add them up with a certain number of weights, and then those weights tell you what the overall Jij couplings you can get. Right? And I think that being visual here is also a really good thing to do. So let's do it. Okay, so what I have plotted here is to say that, let's suppose I have a 7-ion chain. And that means that there are 7 normal modes in my chain. With 7 normal modes, I therefore have 7 basis matrices. Okay, so this one is made out of the center of mass normal modes. This one is made out of the tilt normal modes. This one down here is made out of the zigzag modes. And kind of by our definition, really what we're taking is each normal mode outer product with itself. Okay, so the center of mass mode, where they're all equal in amplitude, I take something that's all, a vector of all ones, and I take an outer product with itself. That becomes a matrix of all ones. Tilt mode, that's the one where the left side is 1 and the right side is -1. Okay, I take an outer product with itself. I got 1 up there in the top left, 1 down here in the top right, but then -1s in the opposite corner. Okay, and I can do this for all of these different modes. And these are kind of like basis matrices that I can construct my Jij's on. And so if I want to build some sort of a Jij matrix, a coupling between spins, I can always express it, using a global beam, I can always express it as some linear combination of these matrices right here. Fair enough? Okay. So, let's say that you wanted to, do, let's say, an all-to-all interaction in a one-dimensional crystal and a two-dimensional crystal. What this tells you is that absolutely, it's something you should be able to do, because exciting an all-to-all interaction means that you want to couple only to this basis function and none others. And so what that means is you have a control problem to solve now. You want to put on all of your different frequency tones in such a way that the coefficient of this center of mass basic matrix is equal to 1, and the coefficient of all of the other modes is equal to 0. When you do that, you excite an all-to-all interaction in a 1D crystal, in an anharmonic crystal, 2D crystal, doesn't matter. Okay. Now, beyond just all-to-all interactions, there are a number of other combinations that you can be interested in. So for instance, we talked about all-to-all interactions in 1D and 2D, but also you can kind of these other interesting interactions. So here I'm calling them dimerized interactions. So in 1D, you can arrange things with still global beams and frequency control, for instance, that you can get these kind of pairs of ions to dimerize and become entangled with each other. If you have a 2D geometry, you can start with kind of a triangular lattice and then make it look like a hexagonal lattice, or trimerized interactions, or kind of a central spin model. All of this by saying, what combinations of these basis matrices should I add up, and then figure out what are all the coefficients that I need to generate them, and then what frequencies do I need to generate those. Okay. Now, I think that there is one question that we started asking, which is to say, how do I know which of these are really accessible? Okay, so I have those set of basis matrices, and now I want to know if I have a particular graph that I'm interested in capturing using these global beams with trapped ions, how do I know if it's accessible or not? And so one of the things that we proved is to say, with global beams, a desired, let me call it J sub desired, is exactly accessible means you can make it if B transpose times J desired times B is equal to a matrix C. Okay, so these B's, these are our normal modes. These are the things that we got from diagonalizing that A matrix all the way back in the first lecture, like an hour ago. Here they are again. And the C on the right, this is a diagonal matrix of these weights, C sub K. Okay, so we really enjoyed seeing this, which is to say, if you have any Jij in mind, can you do this with trapped ions in a given trap configuration? The answer is pretty straightforward. Take your desired Jij interaction, do matrix multiplication by the normal modes that you would find in your trap, and you're going to get an answer. You're going to get a matrix. That matrix is either going to be not diagonal, in which case the answer is can't do it with global beams only, or it is going to be diagonal, in which case the diagonal elements say exactly with what weights you should add up those basis matrices. Okay, it gives you exactly the roadmap how to do it. Right. Questions on that?
So my question was, how do we know that the diagonal matrix will be exactly those CKs? Like, why can't it be some other diagonal matrix?
I guess the answer is based on the way that we have constructed it, based on all of the definitions that have been inherited the whole way through. This is something that kind of came out in our proof of it.
Okay.
Yeah. And so they are kind of one and the same, that if you find a diagonal matrix, then it means it's accessible, and the diagonal elements are that the weights are exactly what you need. Okay.
If it's not exactly diagonal,
Mhm.
just take that diagonal, give you a good approximation.
Yes, it does. I mean, I couldn't have asked for a more beautiful lead into my next slide. So let's take a look at that. Right. So even if it's not exact, is it interesting? Even if it's not exactly diagonal. And this was one of the other big surprises to us too, which is you can do exactly this matrix multiplication that I'm talking about. You can find matrices that are not perfectly diagonal, but they're almost diagonal. And the question is, okay, what is the infidelity between being perfect versus what you can really realize in a system? Okay, so here, let's say that you were interested in getting on the left here, a power law decay of 1 over r to the 1.5 in a 2-dimensional lattice. And here, this is nearest neighbor only interactions. So you can also think of that as like 1 over r to the infinity, right? And you ask, given global beams only, right? I haven't done any individual addressing here, but just given global beams, how well can I do? We've calculated based on how closely you can diagonalize these things, what the rough infidelities that you're looking at are. Okay, so how far away, you're in the kind of 4th digit of precision here. So that means that, it's going to take gates of 99.95% fidelity or so in order for the mapping using global beams onto these, approximate power law decays to be the limiting factor. So you can actually do really spectacularly well, even if the diagonalization is not exact.
Sorry, just out of curiosity, like how many tones you have for, like, say, this many ions? How many tones you have to put?
Yeah, and so now the number of tones that you need is also kind of an experimental question. I would say, the more tones, the better. Usually the, kind of the minimum number that you would need is if you have n normal modes, that you would want to have something of order of kind of 2n, maybe 2n plus 1 tones. And that comes from some details that in phase space, you kind of have real and imaginary parts. And so you want to be able to make sure that, at the end, you have no real nor imaginary parts of phase space extent. And so that gives you a number of degrees of freedom that you have to be constrained by.
Is it like 30, 40?
Yeah, it's if you have n ions, then 2n should be it.
Are your tones always symmetric on the red and blue detuned? And what happens if they are not?
Yeah, so the way that I've built this up, let me take the slide back up here. So the way that I built this up, indeed, all of the tones that we put on, they have symmetric counterparts, right? So every single one is at plus mu1 minus mu1 plus mu2 minus mu2, and they all come in pairs. If these things are not symmetric, that can be very interesting for quantum simulation as well. But effectively, what it does is it adds what looks, from the ion's point of view, to be like a sigma z term. And so what this would be doing would be adding kind of like an Ising model, like a sigma x interaction, plus an additional sigma z, which is proportional to by how much you kind of shifted relative to the other. And in some situations, this might be exactly the kind of model that you want to simulate, and you get it for free. In some situations, you might have wanted an exact Ising model with no transverse field, in which case it's bad news.
So if you don't have a transverse field, is that not a classical model?
Yeah, so far, everything right now, right, this is a classical Ising model still, right? I've talked about the connections, but everything commutes with everything else right now, right? So there are no quantum phase transitions or anything else. We're coming to that.
So just to so is this like if I want to actually make a practical, like I just want to make a quantum computer with trapped ions, do we have transverse fields built in that? Because otherwise I'm just
Absolutely, that's coming.
Okay.
Otherwise, we're working really hard and it's not going anywhere. Okay, I agree.
I have a question regarding like the like transverse field stuff. So, but if you shift like one way, then it's gonna be harder to close the phonon loop, which means that you
Is
actually
it going to be harder to?
close the phonon loop, because like if you have multi-tone, that means like you actually close to the modes, right? Then this phonon error will increase if you shift it one way, right?
Yeah, that's right. So it is easier intellectually to think about it as just having one pair and shifting them is making your sigma z. If all of the pairs are shifting, then they're all making their own contributions to sigma z, and closing the phase space loops become really difficult. I mean, I think you would have enough degrees of freedom to do it, but it's not obvious how to do it. I think you would have to make each of the non-symmetric sidebands now have their own independent probabilities to do it.
I see.
So you have enough parameters, but you have to tune those knobs.
Yeah, I have a question regarding the like how many tones you want to add. It seems to me if you have n modes to tune the overall J, well, why is it helpful to have? Why do you want m like up to 2n? It seems m up to n is kind of enough for engineer and different CK.
Yeah. So the whole key is that I think it was said in the previous question, what it alluded to. It's very easy to think about being in this limit where we're virtually exciting phonons when we have just a single tone and we're far detuned from this whole group of things. As soon as you start trying to put tones and put them kind of in this forest here, then you're necessarily going to start coming into a situation where you can't really, unless you're willing to wait exceptionally long times, you can't really start putting tones in here without exciting phonons. As soon as you start exciting phonons, you now have to worry about closing phase space loops, which is the fancy way of saying you have to make it so that at the particular time that you're stopping your quantum simulation, that all of the entanglement is back in the spin degrees of freedom and not in the motion anymore. Mm-hmm. And that gives you constraints that have to do with, what are the detunings away from the modes, and then what amplitudes have you picked that sets particular constraints. And those constraints have to be sort of respected. And the only way to respect all of those constraints at once is to add more tones to kind of make sure that you have enough degrees of freedom to satisfy all of the constraints.
Thanks.
Okay. So I want to keep going with global beams here because I think it's what should I say? Yeah, I don't want to belabor the point too much here, but I think we're all kind of aware of quantum computation in some sense, and that if you want to build a universal quantum computer, sure, poke every qubit with every laser beam and have full control over everything, then of course you can do arbitrary 2-qubit gates over everything. Here I'm trying to start with, technologically, what is the simplest thing that you could imagine building? And then, layer by layer, add on to the complexity here. So where we've come so far is to say we have a big global beam. We've started with single tones. We've now added multi-tone driving to our big global beam. And now I want to introduce a couple of other tools in the toolbox that still make use of these global beams. Right, and of course, the tools that I'm going to introduce here, I mean, they're going to work in pretty much all the more advanced platforms as well. You know, we'll get to some of the more advanced things we can do with ions, but let me, say how far can we push these global beams entirely? All right, so I want to introduce just kind of two more quick tools to say, how can we expand the power of quantum simulation? And the first tool that I want to introduce is a global rotation. Okay, and so the way that you can apply a global rotation is to couple to the carrier frequency. Okay. So in one sense, if you couple to the carrier frequency, then really this looks like a spin flip transition, right? You drive from spin down to spin up and back again. And depending on the phase of that coupling, you can really look at this as spin precession in an effective magnetic field, either around the x-axis or the y-axis. And so what that does for you is allows you to add terms to your Hamiltonian. So we've already had the sum on Jij, sigma ix, sigma jx. So we already had that. But once we start coupling to the carrier, we can now add a term bx, sum on sigma ix. This is a longitudinal field, plus a term by, sum sigma iy. And this is a transverse field. Okay, so just like the questions before, all of a sudden now we have a quantum Ising model, transverse field Ising model. And what makes it quantum is that we have pieces of this Hamiltonian which do not commute with each other, right? So all of a sudden we've gone from the classical Ising model world into something that, looking at quantum phase transitions and quantum phase diagrams and quantum simulation of this and that, all of a sudden you need a quantum description of your system to handle it. Okay, and we've still done this all with global beams. The second tool that I'll just kind of briefly mention, this one, I'll call it trotterization. Okay, and it's this idea we can make use of the identity that if we have two different Hamiltonians which don't commute with each other, something like e to the minus I h1 plus h2 times time, the time evolution of that system is approximately equal to e to the minus I Hamiltonian 1 times time divided by n times e to the minus I Hamiltonian 2 times time divided by n to the nth power. Okay, in other words, if I have some overall Hamiltonian which has two pieces in it, I can build that Hamiltonian's time evolution approximately by running the first piece just for a little bit, then the second piece just for a little bit, and then cycling that over and over and over and over. Okay, and this is particularly useful because this whole time I've been talking about these Jij interactions as being in the XX direction. But one way to think about it is with global rotations, if all I have is XX, but I also have global rotations, I could take my quantum state, I can apply XX to it, or I could take my quantum state, rotate it, apply XX, and rotate back. And now that looks like YY, or that looks like ZZ, depending on which way I rotate. And so that, combined with trotterization, we can use that to simulate much more complicated Hamiltonians. Okay, so something like an XYZ model, where maybe we sum overall I minus J of some Jij in the X direction, sigma X, plus perhaps a different Jij in the Y direction, sigma Y, and yet another Jij here in the Z direction, sigma Z. All right, so we have some real fundamental tools, right? These are, just an Ising interaction, maybe just a global rotation. And with that, all of a sudden, we can start building things that look like Heisenberg spin models and XYZ models and lots of things that are kind of the bread and butter of difficult problems to solve in condensed matter physics and quantum many-body physics, especially keeping in mind that these Jijs are tunable by building up all of these kind of interaction matrices and that they are all connected. Right, so all of a sudden, somehow we have the ability with these very simple tools to get a lot of quantum simulation power. Let me pause there for questions.
Well, the global rotation, if there's an error in that, will that just spread error like to?
Yeah, so then this is a great question. If there is error in your global rotation, will that spread error, kind of later on in the simulation? Absolutely. So let me talk about when we say easier sources of error to avoid and maybe more difficult ones. So one, let's say that I wanted an XX interaction and then also a YY interaction. One way with ions I could do it would be with a global rotation and then global rotation back. And the infidelity you'd expect is proportional to the infidelity of that global rotation. Probably the better way to do it is this XX interaction that we get in ions comes from the particular phase of that dichromatic beat that we put on. If we change that phase by 90 degrees, then we get a YY interaction. No global rotations necessary. Right? So that's one easy fix that I can do. Okay, but absolutely, when you do global rotations, those errors will occur. The second error that maybe you have to be a little bit aware of is the so-called kind of Trotter error, right? So this approximation here depends sort of like the square of what is the little time step that you do. And then there are higher order Trotter formulas that you might do this one for a time t over 2, and then this one for a time t, and then this one again for a time t over 2. And then repeat that whole sequence. That pushes the error up to that time step cubed. And then there are higher and higher ones to do. And then you have to balance what is the error that you get from chasing shorter time steps versus error that might be in your control hardware. Maybe your beads don't turn on perfectly, in 0 time. Maybe you have some pulse shaping that you have to do there and worry about all those kinds of effects that accompany the switching of things on and off. So it's always an experimental balance there where the error is going to be.
So I'm confused. How is the last hemisphere came from the global rotation and of the total exhibition?
Yeah. So let's say. So what I'm saying here. Let's say I wanted a YY Hamilton, and let's say I'm only able to apply XX in global rotations. Okay. So if I have some spins that are pointing along Y, I can rotate them to be along X. Do my XX, and rotate back. That looks like a Y line. Okay. So now I know how to build this piece. I already knew how to build this piece. I didn't have to do any rotations. I could also now rotate down, get my ZZ and rotate back. And now I know how to build this piece. So you could think about each of these pieces as being its own little subroutine. And so then I apply this one for a little bit of time. I rotate, apply my XX for a little bit of time and rotate back, and I get this. Then I rotate to do ZZ for a little bit of time, rotate back, and then I get this. And then I go back to the start and repeat. And in doing it in that kind of stroboscopic way, that's exactly what we mean by building up this Trotter time sequence. Okay, you apply the first thing for a little bit of time, second thing for a little bit of time, here, third thing for a little bit of time, cycle back and repeat.
So it's in time domain.
Exactly, time domain. Okay, so we've come a pretty long way talking about global beams. And what I'd like to do is to kind of now fill in the last little bit some middle ground between saying we have global beams here, and we've come a long way. We can do some powerful things. Global beams on their own, I have to point out though, they are not universal for computation or simulation. All right, there will be problems out there. There will be unitary evolutions that cannot be captured by global beams on their own. And so, we do know that global beams on their own are not universal. We can imagine what happens if I have local 2-qubit entangling interactions and local single-qubit rotations. That's what Oxford and IonQ and Quantinuum's ion trap quantum computers are all doing, local 2-qubit entanglement and single-qubit rotations. So is there any middle ground? Is there something technologically easier than a $1 billion machine that's also universal? Right? And the answer is yes. And let me talk about that for the last little bit. All right, so now what we'd like to consider is that we still keep our global entangling beams. Okay, so these are still the things that give us Ising in XY, XYZ, all of the JIJ stuff. We're going to keep that, right? All of the work that we've done so far, you still get to use. But now what I'm going to add is instead of having global rotations, now I'm just going to loosen that restriction just a little bit, okay? I'm going to allow for local single qubit rotations. All right, so it's a real small shift. Okay, we had global everything before. We now still allow for global everything, but we're also going to allow the ability to go into individual qubits and rotate, one by itself. Okay, and that's it. And maybe surprisingly, at least to me, I think it's interesting that this is universal. Okay, meaning that any unitary that you might want to evolve, okay, be it some weirdo kind of model in many body physics, maybe some quantum chemistry problem, maybe Shor's algorithm is really your jam, and you just want to do it with global entangling beams and local single qubit rotations. Universality guarantees that there is some decomposition which allows you to do it. There's no guarantee, by the way, that it can be done in sub-exponential time, but there's a guarantee that you can decompose it and run, right? That's what universal means. And with these two ingredients, you have everything that you need. And let me show you kind of two early examples of using global entangling interactions along with single qubit rotations to do something interesting. Okay, so in this first case here, this is a study that we did back in Chris's group and Chris Monroe's group a few years back, where we started looking at the many-body localization of quantum systems. So this is, you should think of an Ising interaction. So you have interactions between all of these different spins, which are fully connected. And then at the same time, kind of competing with these interactions in a way is site-dependent random disorder. Okay, and so what this potential landscape here is telling you something about kind of random disordered strength, which is interacting with these ions, and then kind of you see these really interesting many-body localization effects where the initial wave function kind of has this persistent memory of its initial condition, despite the fact that entanglement is kind of very slowly growing in these systems, and it's generated a lot of buzz and interest in the condensed matter community over the past decade or so. This experiment's only possible when you add those long-range interactions, which we have with ions, with the single site addressing that you need to put on this random disorder, which differs from site to site. Okay, that's not something that you can get with global rotations. And then another kind of flashy result that comes out of these kinds of things. I like showing this example because it puts together a lot of the pieces of things that we've been talking about so far. So this is a trapped ion experiment looking at the emergence of a discrete time crystal. And in this case, you start with global rotations, and we talked about those. We then add global interactions, these Ising models, which we've talked about. And then here, this is where the site-dependent stuff comes in. You also add disorder. Okay, so this is taking a laser beam, hitting different ions with different strengths. And by the way, all of these things, they're not done in parallel, they're done sequentially. This is a trotterized sequence where you do thing 1, then thing 2, then thing 3, all for short periods of time. And then you cycle back to the beginning, and then you kind of do that over and over and over. So it's using all of the kind of toolbox things that we've talked about so far in terms of Ising interactions, global rotations, and trotterization. And now we're adding just this one extra little piece here, which is local site-dependent rotations. And then the amount of power that you get out of that, it opens up a whole world of other kinds of experiments. Right. Questions there?
Can you say experimentally how you do single qubit rotations?
Yeah, so experimentally, the way that we do it let me talk about it very specifically for the ytterbium ions that I work with. You can imagine having an array of your ions, and with that array of ions, ion energy levels, they are particularly sensitive to high power beams that can generate star shifts. And so the laser that we use for entanglement, if we don't control those star shifts, the energy levels kind of split apart. And then that looks like a sigma Z rotation. Okay, and so sometimes that's a bad thing. We want to get that under control. And then occasionally it can be a good thing where we say, maybe we want a local sigma Z operation. And so we can take these entanglement beams, focus them down onto individual ions, and for actually not that much laser power, you can get some appreciable Stark shifts, which count as sigma Z local rotations. Yeah.
Okay. I still got it.
So these ingredients are enough for universality. Why would then these companies that you mentioned invest the money in trying to make it?
So if someone knows the answer, well, there are good reasons. Let me start there. If someone knows the answer to the question I'm about to pose, please come talk to me. It seems to me that there are very specific problems that, gate model all the way, kind of there are efficient decompositions in terms of C-naughts and single qubit rotations and all to do it. It also seems like there are different problems, many of which that are inspired by, let me call them physical systems, condensed matter physics, quantum chemistry, where it seems like a Hamiltonian description of the problem is a more efficient decomposition. Okay. Now, the problem classes, if you hand me kind of an arbitrary problem and ask, is a gate model decomposition more efficient or a Hamiltonian kind of description? I have no idea how to answer that. I think with the gate model stuff, it's known that it's universal. There are really good paths to error correction. And I think if you want to have a 10-year roadmap and get to 1 million qubits, I can really understand a lot of the choices that are being made there. At the same time, I think that there are also lots of other problems out there where a Hamiltonian description and these kind of global operations and all may be better suited for the particular problem of interest. So that's my take on it, but if somebody can say something more concrete than that, I'd love to discuss. Okay. And so just in the last few minutes here, I'd like to give you a framework for how you might decompose kind of arbitrary Ising interactions, right? So what I've talked about so far is to say that we have all these JIJs, we have these basis matrices. I've said that with global beams, some interactions are accessible and others may be approximately accessible, and some may not be accessible at all with global laser beams. But certainly if we add single qubit rotations to the mix, that means that we have something that's universal, and therefore it means that any Ising type interaction, any coupling between pairs of spins I and J that you can think of should be able to be engineered if you have universal interactions. Okay, and so let me give you a framework for how to do it. And this general framework kind of falls under the the heading of digital analog quantum computation. And the idea here is that you do a little bit of analog quantum computation, you let your system evolve in time for a little bit using all these kind of global entangling operations. Then you stop and do some single qubit rotations. Then you let things analog run for a little bit, and you stop, and then you do some of these digital single qubit rotations. And then in doing so, you can build something universal, right? So in this case, let me kind of say that our tools are some Ising interaction, some on Jij, sigma Ix, sigma Ij, and this is an all-to-all interaction. Okay, so all you need here is a fully connected Hamiltonian for this to work. And then the second tool that you need is a local Z pi gate. Okay, in other words, have the ability to flip a spin along the Z direction by pi, but pick which spin you want to flip. Okay. And so if we count them up, in this Jij matrix, between n ions, there are n times n minus 1 over 2 independent couplings. Okay, and by couplings, I mean J12, J13, J14, J23, J24. Okay, so if you count up how many pairs of couplings you have for n ions, you have n times n minus 1 over 2. The protocol for this digital analog quantum computation is as follows. So I'm going to draw this kind of like in a circuit model thing. You start with local Z rotations, let's say on campus 1 and 2. Then you evolve with your Jij. Okay, the Jij that you have in this global entangling interaction. And then you apply more single qubit rotations on 1 and 2. As the next step, you do the same thing, but now for qubits 1 and 3. And then you evolve with your Jij. And you kind of keep doing this until you hit every pair. 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, and so on. The key here is that you evolve here for a time T1, evolve here for a time T2, and so on. And you do this for n times n minus 1 over 2 times. And that gives you enough data freedom to go in and specify all n times n minus 1 over 2 elements in the Jij matrix. So no matter what Jij you're given, as long as it's fully connected, like it is in trapped ions, that fully connected Jij coupled with these single qubit rotations allows you to build any other arbitrary Jij you'd be interested in. Okay, so this has fantastic power for many-body physics, chemistry, optimization problems, all of the usual suspects when it comes to quantum simulation of Ising models. This is a way of going from what the ion trap system gives you natively to something that might be kind of an exact match for the problem that you're interested in. And really all it takes to do it is to have your global entangling operations, which are a really straightforward thing to do with trapped ion systems, and then sprinkle in these single qubit rotations and pairs where needed. Okay, so to kind of recap where we've gone, right? We've started from this lowly 1940s technology, the ion trap, some charged particle that we use kind of electric fields, oscillating and DC electric fields to trap. We've gone all the way to the normal modes and how that informed how these ions could be coupled in the qubit subspaces. And then with those couplings between light and ions, those interactions can be built to do things that look like Ising models, XY models, Hamiltonians that are even more complicated, all the way to universal kind of Hamiltonians with the addition of single qubit rotations. So I really had a lot of fun telling you about some of the ways that we can engineer these ion trap systems, and I'm happy to keep discussing with you now in the questions or over dinners, lunches, meals, and ice cream later. Thanks again.
You have a question?
So what,
Thank you very much for the talk. So you said that this approximation, this Ising approximation is true in this like large detuning limit. Is that right? Can you remind me again, what was the intuition for that?
Yeah, so let me say it more specifically. The Ising approximation is true in the limit that when you are done with your quantum simulation, you have zero or near zero quantum information left in the phonon degrees of freedom. There's two ways to accomplish that. One way is so that you're always so far away detuned from the vibrational modes that you could stop anywhere and you never actually accumulated all that much, or at least you never got too much motion, you just accumulated it for a long time. The other way to do it is to go faster and be less detuned and make sure that you stop your simulation at a very particular time. Okay, so either is fine. The whole goal of that approximation to hold is that you want no information left in the phonons at the end of a simulation.
That'll be our last question.
Hi, I'm just wondering, is there any reason that prevents you to have like both XX interaction and ZZ interaction simultaneously?
An XX and a ZZ simultaneously, did you say?
Yeah, like instead of doing any like polarization and rotation and stuff.
Yeah, so let's see. There are ways of doing something that looks like it. So this gets a little technical, but one of the things that that people have done in the past is, let's say you have an XX interaction and you put on a very strong global beam that looks like a very strong effective Y field. Okay. Then effectively what you get is that spin flip transitions are energetically disallowed. Okay, so if you have kind of, in the Y subspace, if you have kind of no excitation along Y, then making a Y excitation there costs a lot of energy if you have a very strong Y magnetic field. So what that does is turns the XX model into a sigma plus sigma minus model. It conserves the number of excitations that you have. And if you then take XX plus very, very large B and say that that's equivalent to sigma plus sigma minus plus Hermitian conjugate, and then work that back into Pauli directions, you kind of magically get XX plus YY. And those interactions have been used without any additional phases or anything else to look at XY physics.
I see. So if that kind of scheme, do you need to like have the strength of the Y field to scale with the number of ions that you have?
Yeah. So in that case, you mean the strength of the magnetic field?
Yeah.
So in that case, it does not need to scale with the number of ions that you have, because any one of them flipping would be energetically disfavored.
Okay. Thank you.
With that, let's thank Professor Bill Richerme once again.